Okay, thank you very much, Camilo, for the nice invitation. It's really an honor to speak here. And but I have to thank also Lia Vrue, was not here anymore now, but they contacted me first last semester, but they couldn't come. And so today I will talk a little bit about basically advection diffusion equations for general velocity fields. Autonomous velocity fields, but I want to start with a little bit with the motivation for this work, which is really coming from hydrodynamic stability. So I'll start about the motivation comes from looking at the long-time behavior of 2D Euler and Navier-Stokes equations. So I'm looking at the following equation. So omega here is the vorticity of an incompressible fluid. And U is given by the gradient perp of the stream function psi, and Laplacian of psi is equal to. So U is really the velocity of Navier-Stokes, and psi is the stream function. And I'm looking at also the case of Euler, so that's the parameter nu, the viscosity, kinematic viscosity can be also 0. Okay. So the question of well-posedness in 2 dimensions is not a problem. Smooth solutions, I mean, smooth data originate smooth solutions, and they stay smooth for all times. So the next question is what do solutions do for time going to infinity? Okay, so do I move to the UK? I still keep the American spelling of all these words.
Which spatial domain are you going to be?
So the spatial domain here, I can think of things without boundaries, so maybe the periodic box or the infinite periodic strip. For Euler, it doesn't really matter. I can also put a bounded channel here, but I don't want to deal with boundary conditions for the vorticity, so let's not do that. And okay, so for nu equals 0, really the conjecture that is formulated by Zverak in his lecture notes on fluids, but it can be traced back also to some work of Schneermann as well, is that solutions, so generically, omega of t converges weakly in L2, and not strongly to a steady state. Or maybe a slightly more complicated structure, maybe a traveling wave solution or something like that. But let's just keep it in these terms. And so, so this conjecture is very complicated to prove, especially because for nu equals 0, we have a conservative equation and you don't have any sort of obvious global dissipation mechanism. But at least intuitively, what does this conjecture tell you? It tells you that Euler creates some sort of oscillations or small scales that create an averaging mechanism, if you like. So weak convergence is typically associated to weak convergence type. Weak convergence is associated to averaging type phenomena, and you cannot expect any strong convergence because again, equations are conservative, so they conserve the L2 norm. Okay, so the main mechanism to be detected is some sort of averaging that which can be understood as creation of small scales. And in fact, this is what I typically think of when I think of mixing. Okay. So how can one approach this conjecture? Again, generically, I don't even want to talk about the meaning of this word, really. It's maybe loosely stated. But again, this conjecture is extremely hard, but one can try at least to approach it in several ways. One is to try to understand, for example, what are the steady states for this equation, right? First of all, if you want to prove that something converges to a structure, an endpoint configuration, then you would like to understand what are those. That's one thing. I won't talk too much about it. I want to talk about the dynamical problem. And so the other approach is try to prove something perturbatively. So basically, what we're going to look at is a steady state.
It converges weakly but strongly.
But not strongly. Sorry. I forgot the.
I couldn't understand the statement.
You're perfectly right. It didn't make any sense. So yeah. Not strong.
Actually, while we're interrupting, sorry.
Yeah.
So what's the more I don't know, like adult statement? Because like on the torus, when you have a traveling vortex pair, it's not really a steady state.
So I think what the real statement is that Euler converges to something whose trajectory is compact.
Okay.
Okay. So a steady state is just a point. It is what it is, but it converges weakly to something that has a compact trajectory.
Okay.
I think that's the statement that comes from Schneerman, sort of version of the conjecture. So if we look at steady states, so I'm just going to denote this by omega E for equilibrium, okay, and the corresponding velocity and stream function. And we can write the solution omega as your steady state plus little omega, and try to understand what the little omega does. So if I write down the equation for little omega is the following. So I have a quadratic nonlinearity. So this will give me two terms. So small letters are what refers to the perturbation. And let me write it equation of omega minus. So I have a linearized operator, which is coming from transport and diffusion, and I have the nonlinear term. Okay. So what can we say about this problem? Well, we can say something in very particular cases, which I will tell you a little bit about. But in principle, you'll agree with me that at least if we forget about this term and the nonlinear term, we need to really understand what happens for the corresponding advection diffusion equation. Okay? So this is my motivation to study, if you want, the diffusion equation. But in general, this term, they being a compact perturbation of the rest, it's really not just treated as a perturbation. It can have a very big influence on the dynamics as well. Okay, so let me tell you about a couple of results. So what are the possible steady states that we can look at? Okay, so one steady state that is typically looked at is that of shear flows. And these are, if you like, Hamiltonian flows, where the Hamiltonian is the psi, the stream function, in which the stream function depends only on one of the two variables. Okay, so typically they're written more like, let's see, this way. There are steady states in which the streamlines of the corresponding Hamiltonian are horizontal lines. And well, if V is non-constant, the particle of the fluids, they move at different speed. And so they create this shear mechanism among these two. So let's say something. Okay. So for shear flows, one can write down the equation, and in some cases you can say something about how omega behaves as time goes to infinity. I'll tell you the result in a minute. Other typical, so these shear flows, the spatial domain is typically 0, 1 or t plus r. So one variable will always be periodic for me, okay? So in this case, the x variable. Radial flows. Okay, here, let me just maybe write the stream function only depends on the radius. So here you can think of being in a disk or in the whole space. And of course, the streamlines are well, circles. And well, if you think of r theta, here you can be again in a disk. And theta is the x in this case, if you look at the linearized problem. But of course, these are not all the possible solutions to the Euler. There are many more. And the third kind of stationary solutions that I'm more interested in today are the ones that satisfy an equation of this type. So it's very easy to see that if f says C1, all these solutions are stationary solutions for Euler, just because if you compute the gradient of omega, this is your vorticity really. The gradient of omega is just f prime times the gradient of psi, and u is the gradient perp of psi. So that gives you 0. Okay, these are stationary solutions to Euler. And one example, right, is eigenfunctions of the Laplacian. This is the, if you want, simple example of solutions of this type. But okay, there are some shear flows that are also solutions of this equation. Think of sine y, for example. The so-called Kolmogorov flow is an eigenfunction of the Laplacian. But there are more complicated ones, and you don't have to think too hard. But if you just think of sine x plus sine y, this is not a shear flow, and it doesn't have streamlines that are as simple as this. So something that can happen is that streamlines, let's say on the periodic box, they can look like so-called cellular. So these are something that look like this. And on the separatrices here, if you want, if you're thinking of already of the flow generated by something like this, you have some exponential compression, exponential stretching. You have some something that resembles rotation here, and then you of course have some points, the elliptic points of the Hamiltonian that are also special. So you have hyperbolic points at the origin, let's say here. This is what I'm drawing is really sine x times sine y, okay? Sine x plus sine y is just a rotation by 45 degrees of this. So this is the example I'm looking at. And so while for these two flows, we know at least a little bit about the dynamics of Euler near them, near something like this, we really don't know very much, okay? So what I want to tell you about is how do I deal with flows like this, even in the simplest case in which I just look at the passive scalar where the velocity field is given by something Hamiltonian that we it's looking like this. What are the known results for, say, shear flows? So, and these are results that are that started at least at the nonlinear level with the work of Bedros and Masmoudi. I think now 10 years ago. And then there are more recent work by UNESCO, and also Masmoudi and Derenzau. So I can state the result in full glory, but it will take me a couple of boards, I think, to put all the parameters correctly. So the main assumption is that we are in shear flows and V prime, so V is a monotone here. For Bedros and Masmoudi is really V of y equal y, the correct flow. But these works of UNESCO and GM Masmoudi et al. Extended to more general flows that still keep the monotonicity, but for which the second derivative doesn't necessarily have to be small. So they're not really close, saying C2 to the coed flow. And the way I will just state this result is that really the perturbation of the velocity u converges strongly to some profile that is really a shear flow. Okay, and you can write down the rates at which this happened. And okay, I talked about weak convergence, and now I'm telling you strong convergence, but this is strong convergence of u, of the velocity, which the velocity is one derivative more regular than the vorticity. So this is kind of an h-1 statement about the vorticity. Okay, so it's an h-1 statement of the vorticity, which is equivalent to weak convergence of in L2 of the vorticity. So the statement is that for small perturbations, so for initial data that are small in some infinite regularity spaces, reference spaces, you do have this convergence of the perturbation. So near, and this limiting state is a shear flow that is near the base flow that you started. Okay, so now what can we say? There are some more results about, there is one more result by UNESCO and GIA on the point vortex, so when the vorticity is a delta function. But okay, that's the only sort of radial type result. Okay, so the talk of today is really about the baby version of this problem, but for a more complicated flow. Okay, so what I will look at is diffusion. And of course, I haven't told you anything about Navier-Stokes up to now. There are some interesting results also in that case, but I will just tell you about results with diffusion in the context of linear problems. So here I'm looking more at a problem of this type. Okay, now rho is passively transported by a vector field B. So B is the gradient perp of a Hamiltonian H. So B is divergence free and diffused with the diffusion coefficient equal to nu. And so the question is, what can we expect from these problems? And so let me just give you two definitions. So one is mixing. So B is mixing at rate gamma. T is rho of T H minus 1 is less than or equal to gamma of t 0. 1 or 0, it is the initial datum for every t positive. Gamma is a continuous monotone decreasing function that vanishes at infinity. Okay, so let's just okay. So this mixing, and so you see here quantify mixing by a negative Sobolev norm, and similarly, and here I should say maybe nu is equal to 0, and definition 2 is I'm looking at nu positive. And so I denote maybe the solution that exists. So let's say B is dissipation enhancing. Iterate lambda nu for now. I have to tell you what is this. The rate lambda nu has to be compared with nu in this way. So I'm giving myself an increasing function lambda such that nu over lambda of nu is equal to 0. So near 0, the vanishing of lambda is much slower than nu. Okay, so that's what I'm saying here. If rho nu of t, solution to the fraction diffusion equation, is less than or equal e to the minus lambda nu t. And this is for every rho 0 in H1, and this is for every rho 0 in L2, say with mean 0, if I'm on the torus. Now, one thing about this definition is that there is a clear set of initial data that will not satisfy these definitions. And those are the ones that are, say, function of the Hamiltonian, right? So if I take H as my initial datum and I plug in H in here, right, B dot grad H is 0. So all the time in this talk, I will assume that rho 0 as vanishing average on level sets or on streamlines. Okay, so if you want the initial, I just take this condition as true in all of this. Now, these definitions make sense because.
So your estimate has to be true for every rho 0 with this property.
Yes, yes. So it's a universal estimate in this sense. Exactly. Okay, so this definition we talked a little bit about before, why it makes sense to say that the H-1 norm decay for a transfer problem in which the velocity field creates small scales. What about enhanced dissipation or enhanced diffusion? Well, I'm just saying that instead of the solution, instead of decaying like the heat equation would tell me to, so e to the minus nu t, I am decaying much faster than that. Why is that? Well, because I'm creating small scales, and when I create small scales through B, that's when the diffusion is most efficient. So the intuition behind this is that, when I created enough small scales, then the diffusion will be very, very efficient and will just make everything decay at a faster time scale. Okay.
The hidden constant there may depend on the initial condition.
No. This is just so. I wanted to write the definition a little bit. So this is some constant independent of anything. It depends on B, if you want. It could depend on B. Yes. I really want a semi-group estimate, right? L2 to L2 estimate for the semi-group generated by this guy. Okay, so this problem has been studied for a long time in the applied literature. There is a nice paper by Rines and Young in 1983, I think, that asked, the title is really how fast is a passive scalar mixed by closed streamlines. And the answer they give is nu to the 1/3. So lambda of nu is nu to the 1/3. That's basically the answer that they get. So let me tell you just where does this nu to the 1/3 come from?
Is this a heuristic or?
It's so I gave a precise meaning as to why they say no to the 1/3, but it's not really proven. It's a heuristic, yes. So
It's not strictly true.
it's not strictly true either. So that's
Counter example.
yeah. So it doesn't have to be as fast as nu to the 1/3. It can be slower.
Okay.
But well, if you take this definition, which is not precisely written in that paper, so this definition was phrased essentially by Peter Constantine and collaborators in 2008. Okay, so the definition, one may think that for a certain set of initial data, you really have nu to the 1/3 always, and that's kind of true.
Okay.
But so again, and this is the last time I mentioned shear flows because I promised you to talk about something else. But for shear flows, we really can say something precise. So again, remember that D is V of Y0. Okay. So the function D can be anything, and in particular, it can have, well, let's say with a certain degree of regularity, can have critical points. So the only number that I care about is the maximal order of vanishing at critical points. So what I want to say is that you may have a critical point, and this goes like y minus y critical. So all the derivatives before the nth one, they vanish. So for n is equal to 2 if you have a critical point at least, right? Because so n equal 1, think of it as being just mod the shear, okay? So there is no critical point. So this is for n greater than or equal to 2. So I can tell you that gamma of t in this case, so this is a result that I proved with Jacob and then Bedrosian, and there is work by Dallas as well, and work by Thierry Gallet. The mixing rate is t to the 1/n, and the enhanced dissipation rate is nu to the n+1/n+3. So what is important here is that, so here, well, is whatever rate we get. Notice that as n grows, so the flatter the critical points, the slower the mixing, okay? This is something that was known, I think, also a long time ago in the physics literature. Now, lambda of nu, the important thing is that this exponent is less than 1, so that it complies with the definition that I gave there, okay? It's bigger than nu, for nu small. As n goes to infinity, this goes exactly to 1, which is the heat equation rate. And that tells me that, okay, there is no enhanced dissipation if I have too flat of a critical point. And these are sharp, so this is really upper and lower bounds, okay, for this type of flows. So you see that if now I wrote it in sorry, I wrote it in yes. So n equal 1, I have 1/3.
So if it is monotone,
If it is monotone, I have 1/3.
exactly.
No to the 1/3, which is what Reinse-Young sort of wrote. But you see that if not monotone, so if I have, say, on the torus, for example, it can't be monotone if you're regular. And so n has to be at least 2. And so you get nu to the 1/2. Okay. So similar result holds for circular flows. Okay, you can prove a similar thing. So how do we prove something like this? So let me not talk about how do you prove enhanced dissipation, which is a bit more complicated, but it's important to at least understand how to prove the mixing one. And I mean, that's something that, sorry, roll. This is my equation. My transport equation. And if I just take a Fourier transform in the x variable, which I can, it's just Fourier series because x is periodic, then I get ikd of y rho hat 0, and I can just solve this. It's e to the minus ikd of y t rho 0. Okay, and so now you see exactly where this averaging intuition comes from. If I integrate this is an oscillatory integral, and effective v of y is really just y. It's precisely the Fourier transform of this function at kt in the other variable, the Fourier. So we know that if we pay irregularity, the Fourier transform will decay. So if we only pay one derivative, it will decay like 1 over t. It will decay like 1 over t. And if you pay 3 derivatives, it will decay like 1 over t cubed. But you will have an h minus 3 estimate at that point. And the definition that they gave you is with h minus 1 on it. Okay. So I want to only pay one derivative. However, if you have critical points and you think about the stationary phase argument, it doesn't matter how many derivatives you pay at that point. You can pay 3 derivatives, but you still are stuck with a certain amount of decay that it depends on the order of vanishing of the critical points, because V is the phase of this oscillatory term. Okay, so there it depends also whether the initial datum really is 0, where this phase is stationary or not. Right? That's how the decay is. The maximal decay, if you want, is restored, but. This is what drives this rate. Okay. Now, what happens with Hamiltonian flows? So in general, so if I have V equals so the idea is that we may have closed and open streamlines, but for sure, if we're on a compact space, I'm thinking of the torus, but you can do this on a more general manifold. You will have a minimum, and so you will have some closed orbits, let's say, so near an elliptic point. Okay, and so the idea is that the question is, can I reduce myself to this problem somehow, so that I know how to compute mixing rates. Okay, this is a sort of a strategy that could be used. And the point is that you would like to find at least an invariant domain. Maybe you cannot have a transformation that brings you here everywhere in the domain, right? If you think of having hyperbolic and elliptic points, there may be degeneracies. But maybe some good domain you can find this type of transformation. So so the key observation. So let me just tell you what the result is in general for what I can tell you for general Hamiltonian flows. So the theorem with, so this is a joint work with Elia Brouet and Elio Acconi. In Padova. Sort of giving a meaning to this paper of Rice and Young in the 80s in terms of a general Hamiltonian flow. So there are two estimates, one on mixing and one on dissipation. So the mixing estimate is really from a paper Bonicato-Marconi, in 2019, and one is by Elia. Start from video. Means that if you have a certain regularity for the Hamiltonian, so H has to be C1 intersection W1P, or let's say P greater than or equal to 2. Marconi. So what we have is that gamma of T is greater than or equal 1 over T. So this is really the result of Bonicato-Marconi. And lambda nu is less than or equal nu to the. Okay. So this is the result I want to talk a little bit about now, and I'll tell you some upgrades of this result by using really the Hamiltonian structure and maybe some more information about it. So let me tell you what are the key observations that for which you can prove this result.
The bracket around T?
Yeah, sorry, bracket.
Like 1 plus.
Yeah, 1 plus.
Okay.
No, of course. Yeah, it's an estimate after T greater.
Yeah, it's an estimate for T large. That's
Yeah,
what you say.
exactly. So let's think of having a, so for this result, in fact, P greater than or equal to 1 is enough. For this one, I need P greater than or equal to 2 because at some point I want to use the energy inequality of the diffusion equation. That tells me that I need to know something about the gradient of the solution in L2. And so that's where the P equal to 2 comes into play there. Okay, so what's the first observation? Is that there exists a good invariant domain for this problem. So let's say there exists constants C0 positive and an interval within the range of H such that first omega, which is the inverse image of this interval, is invariant for the characteristics associated, the characteristic flow associated to this problem. So for the flow dt x is equal to b. Okay, it's invariant for this. So there exists this, of course, this omega has nothing to do with the vorticity. Sorry for using the same letter. And two, that the velocity there is bigger than this constant. Okay. If you think about the cellular flow, you could just do it directly. You really look at the stream function, and the level sets.
So it's annulus around the elliptic point.
You want to stay away from the hyperbolic point, or you want to stay away from the elliptic point. That's it. And in fact, you can just get as close as you want as from the hyperbolic point and the elliptic point, okay? Of course, something will degenerate, like this constant degenerate. That's something important. So in general, well, you have to use some maybe slightly more sophisticated tools, just SARD property type of the critical values of the Hamiltonian. These are a small set. They have zero Lebesgue measure, and the complement of that will be an open set, and you can, by continuity of B, that's why I need C1. One of the places I need to C1, I can find one point for which this happens, and then it's around it for which it's really. Okay, so what I'm trying to hint here is that in this good invariant domain, basically only shearing in the right coordinates is possible. So the phenomenon that I will witness is exactly the same as that of a shear flow, or of a, better said, of a radial flow that has no vanishing velocity. Okay. So the way to really say this is looking at this called action angle variables for this Hamiltonian. So in general, if you have hyperbolic and elliptic points, these action angle coordinates will degenerate at those points. So I don't really know how to do it in a global way, but I can try to do it locally, and locally I mean exactly in this domain. So okay, so let me check. Okay. So the idea is that the action angle variables, they will bring x, say in T2, to say theta and h, where this is in T cross this interval H0, H1. And really the flow in these coordinates look as simple as possible. So in fact, H dot is 0, is constant this is the action, and the angle just grows linearly. Okay, that's precisely what happens in polar coordinates for the radial flow. Okay, so that's exactly what happens here. And all you need to do really is to be able to define the period around the closed orbit. So this is the period of closed orbit h equal little h of a particle that's like of the flow here, right? So, and this is defined as maybe these I have to intersect within my invariant domain, okay? But it's defined as one over the velocity field integrated on this one-dimensional curve. Okay, so this formula is simple, but it doesn't tell you much unless you can really compute something about the period, okay? So, and in general, we don't know really how to compute, but we can try to make some assumptions on the period so that we can just get some enhanced dissipation or some mixing out of it, okay? So, in general, how do we prove this result though? It's not very hard, because what we know now is that essentially in these coordinates, the flow grows linearly in time. So that's what these coordinates do. And if I am in my invariant domain, also the map that changes coordinate is C1 and invertible, and the inverse is also C1. Okay. So really what I get out of these coordinates is that, well, if I change coordinates, first of all, this is what my transport equation looks like in these coordinates. Okay, so from a complicated 2D Hamiltonian flow, I reduce myself to sort of a shear looking like equation. Okay, and so what I get essentially is that the gradient of rho time p is bounded by 1 plus t of say 0. So this is the first estimate that I get, of course, for rho 0 supported. So any initial datum now, so think of again an initial datum that is supported away from an elliptic and a hyperbolic point, and the growth is at most linear in time. Okay. So now, how do I prove? So this already proves the first estimate, because if I have initial data that grow at most like linear in time, by interpolation, I can just say that because the L2 norm is conserved, and the H-1 norm, if I take p equal to 2 there, can decay as at most like 1 over t. This, of course, I'm talking about, universally, like there could be initial data that really decay maybe faster, but we don't really know about this effect. Now, how do I do the enhanced dissipation rate? Let me just tell you what is the key estimate. Essentially, I have my diffusion problem and my non-diffusive, my transport equation. Okay, I have this problem, and then I have this problem, and I want to understand how close are these two problems. Of course, they cannot be close forever, because well, this one conserves the L2 norm, this one the case is exponential the L2 norm. So there's no way this will be close forever, but maybe before dissipation really kicks in, they're close. So if the estimate is really just L2 estimate for the difference of these two problems, okay, so I simply get that I have nu Laplacian of nu times rho. Okay, so if I integrate by parts, right? So I get minus nu gradient of nu squared plus nu times gradient of nu times gradient of rho. So I can absorb half of this in here, and I get that the distance between the two problems is controlled, if they start with the same initial data, is controlled by the integral in time of something that I know how to compute because it's written there. Yeah, well, yeah, over there. Okay. So what I am saying is that rho nu p now 2 squared is less than or equal to from 0 to t. And well, this is, I'm going to have to square there. So I really get nu 1 plus t cubed gradient of rho 0 and n. Okay. So you see here, again, the relation between nu and t is still this nu to the minus 1/3 when I make it 1, okay? So it's exactly this time scale here. And well, what this is just saying is that if I have that rho nu t decays at the some exponential rate, well, that rate cannot be much faster than nu to the nu to the 1/3. Okay, so if I know that rho of nu is less than or equal a into the lambda minus lambda nu t, I know that. So if let me just write it. If I take the fact that rho is conserved in L2, and this is less than or equal rho nu. And this has to be less than or equal than this. So again, just now it's a matter of constructing an initial datum that has norms about 1, all of them. And this tells you that, okay, if lambda of nu was much faster than nu to the 1/3, much bigger than nu to the 1/3, then I can just pick an intermediate time between nu to the minus 1/3 and nu to the 1 over lambda nu, and make this 0, but this still 1.
Why aren't you using a square root?
No, I'm not.
Yeah, there should be a squared in the upper range.
There is a square here.
Okay.
Yeah, it's a linear problem, and they better be all linear.
Yeah.
Yes.
Yes. Okay.
Okay, so this is essentially the argument for the nu to the 1/3. Now, I think I have maybe 5 minutes, so let me tell you what we can say about cellular flows and what we can say about. For now, I haven't really talked about elliptic points, but our work was really meant to understand, what happens when you have elliptic points and hyperbolic points. And so I want to state 2 things. One is, so suppose that you have an elliptic point, say at the origin of your flow. Okay. So what I'm going to do, I'm just going to take this point is say R in 1, and I'm gonna, and to this I have a period T of R associated to how fast this point loop goes around this orbit, which is nothing but. So I like to state the theorem in terms of T of R. So how fast does a point distance R on my Hamiltonian orbit rotates, takes to do 1 period. So if we assume, okay, that T prime of R is like R to the beta, okay, then gamma of T can be at most 1 over T. I need to look up the exponent because to the 2 over 1 plus beta, and lambda nu is nu to the 1 plus beta over 3 plus beta. So, okay, so in the case beta equals 0, this result is not really good in the sense that the result by Bonicato Marconi tells us that in fact it's 1 over T, the lower bound, not really 1 over T squared. Okay, but for beta, say greater than or equal to 1, this is an improvement on that result. And in particular, one may wonder, do you have any examples of something that has a period that is not, whose derivative degenerates like R to some power? And the cellular flow is one of those. Okay, so and I'll tell you why in a second. But this result is proven simply by keeping track of how the gradient of the flow map grows in terms of the constant, in terms of T prime of R. So the result that we have is that the gradient of the flow map W1P is R. Okay, so it's still linear growth, but the linear growth depends on the distance of your initial point from the elliptic point. Okay, so in particular, R to the beta, if you have beta greater than 1, it does slow down the growth a little bit. So the game is then to get an initial datum that is supported within a small distance of the elliptic point and reevaluate the integral from 0 to t of gradient of rho. And if you think of having an estimate of, well, actually, yeah, an estimate of this type, you can estimate the growth a little bit more precisely. Okay, so, and you will get something like this. So for the cellular flow, what can we prove? We can prove that gamma of t is 1 over t to the 1/3 minus. This estimate we knew already. And so cellular flow, I mean that h is really sine x sine y. And nothing else really, and I'll tell you why. And that lambda of nu is nu to the 1/2, because beta is really 1 for the cellular flow. And well, I had the theorem with Tarek El-Gindi and Matthias Delgadino that as soon as you have a mixing rate, you can apply the theorem as a black box and you get an enhanced dissipation rate. And so if you just use that theorem here, you get nu to the 6/7. So it is sharp or not sharp. It's unclear, probably not. I mean, I guess here you get plus, so slightly up to an epsilon, you get this. So it's pretty far from one another. It's unclear that this is sharp, and this one should be the sharp one, really, but we cannot get any closer to that. And the problem is that here, really, you would like to apply the stationary phase lemma to this period, I mean, to this problem with the period in it. So dt rho plus 1 over t. And the period t, you know how it degenerates at the elliptic point and the critical point, and the hyperbolic point. So near the elliptic point, in fact, the mixing is kind of like 1 over t, really. So it doesn't degenerate there. And the problem is at the hyperbolic point, which is somewhat counterintuitive because the hyperbolic point is where you have exponential stretching, exponential compression. And so you would say mixing there is the fastest possible. But the problem is that we lose control of everything. And this, of course, comes exactly from that. So for the cellular flow, the real point is that you can actually compute the period precisely. So I just finished by reading you the formula. Is that for the cellular flow, P of H is for the integral from H to 1 of 1 over square root of x squared minus H squared, 1 over square root of 1 minus. So it's a formula that I mean I wasn't able to find really in the literature, but it could be that it is there, and it's called an elliptic integral of the first kind, incomplete elliptic integral. So not that it is really important that it's a known function, but this we can really compute what the asymptotics are. Effect of these integrals as h goes to 0 or 1. So h0 is the hyperbolic point, h equal 1 is the elliptic point. You know exactly all the asymptotics. Okay, so t of h is less than or equal 1 plus log h, for example. Expected because you have some exponential compression near the elliptic point, the hyperbolic point, and then you have some estimates. Exactly what you would expect, something like 1 over h, and 1 over h squared. So the game is then to use the stationary phase argument, compute precisely all the constants that are involved there, that are related to integrability properties of t or t prime or t double prime, and close the estimates away from the hyperbolic and elliptic point, and near them you just use the smallest of the interval that you're punching out from this. So I think I'm almost done. I'll stop here. What I wanted to say is that what are the consequences for the stability problem for Euler and Navier-Stokes? So it's not clear. What we can say is probably if you're looking for a sort of a convergence rate to a steady state, you shouldn't be able to find something that is faster than 1 over t, also for Euler. Okay, it's unlikely that the non-local term that you have in Euler will just jump the convergence to exponential or something like that. Although you know that solutions to Euler can grow even double exponentially fast. And similar for Navier-Stokes, cellular flows are not solutions for Navier-Stokes, but if you just multiply by an exponential factor like e to the minus lambda nu t, where lambda is the eigenvalue of the cellular flow, so 2 in this case, they are exact solutions to Navier-Stokes, and you can sort of try to think whether these are local attractors for the dynamic of Navier-Stokes, or they're like quasi-stationary solutions. And this tells you that more or less the rates that you can expect are somewhere between this problem. Thank you very much.
Questions? So say that I tell you that this Hamiltonian H is a Morse function, so that you know at all the points that everything is nice. Is that going to help you to carry on this procedure?
So if you have a Morse function, so it's unclear that we asked ourselves this question. I'm not sure if t prime. So you can have a precise beta. Now I don't see where it could. But so what is the behavior of t prime is equal r to the beta? Is there a beta, a universal beta for any Morse function? I'm not sure. I thought it was 1, but I couldn't really prove what is the derivative on the period. However, of course, if you I think mixing, you should be able to, in general, improve that because you don't have a hyperbolic point. So I would expect that you would get, let's say.
That is away from hyperbolic points.
Yes,
you're doing that.
So you should be able to get one of it.
So you have at least one elliptic point, and then.
Yes. But I mean, having a Morse function that doesn't really matter in general if you want to prove lower bound on mixing rate or upper bound. So this doesn't help. It could help to prove that the NAS dissipation rate is really due to the 1/2. If you have like a higher dimensional cellular shear flow, and the shear is a Morse function, then I can prove to you that you really have n to the 1/2. But basically your flow then becomes, it's a higher dimensional thing, and you have v of y, where y now is like n-1 variables, and 0 in, and if v is a Morse function, I can prove to you you get n to the 1/2. But the higher dimensional problem is much harder, even just for shear flows, in fact.
Well, if there are no other questions, thanks.
Thank you.